In this lecture, I would sketch the proof of our two results. The first one is as follows. Let omega be a convex domain satisfying first, the area is equal to that of a unit disk, and omega is symmetric with respect to x-axis and y-axis. Third, the boundary of omega has exactly four vertices. You can think omega as an ellipse. Then the conjecture holds for omega, namely, the isoperimetric profile of omega is bounded from above by that of the unit disk. And the equality holds only if omega equals B1. The setup is shown in this picture. Here, omega is a convex domain satisfying the assumption of the theorem. We assume that the major axis lies on the x-axis. Okay. So for omega, Ionin-Pestov inequality implies that the maximum curvature, which is at the major axis, has curvature greater than 1, and the minimum curvature, which is on the minor axis, is less than 1. These curvature estimates can be translated into the fact that the length of the major axis is greater than 2, and the length of minor axis is less than 2, with some works. And we parameterize the boundary of omega by the unit normal, and then parameterize the symmetric perfect arcs of omega by their endpoints. The symmetric perfect arcs are drew here. Okay. With some works, one can show that they are the minimizer for the isoperimetric problem. But here we only need the trivial fact that they serve as an upper bound for the isoperimetric profile. So therefore, if the lengths of these perfect arcs are bounded from above by the corresponding quantity in unit disk, we will get the comparison for the isoperimetric profile. Let's begin with a lemma. If there are two angles, theta and theta star, then the length of the perfect arc with normal cosine theta, sine theta is less than that in the unit disk of theta star. Okay. Here, this star means that we are computing the quantity in the unit disk, the model case. This picture depicts the situation. On the left, we have omega. On the right, we have the unit disk. And we want to compare the length of these two perfect arcs. So first, we notice that since L is an increasing function of theta, so it suffices to show that when the normal points to the same direction, the corresponding perfect arcs have the desired inequality. Yeah. And we will study the length, not directly, but study the y coordinates on the boundary first. Okay. So, and we have to use the following simple relation. We know that the unit tangent is given by dx ds, dy ds. And since n is the rotation of t, we get n equals dy ds, dx ds. From our definition, it's equal to cosine theta sine theta. And we also know that the curvature is the derivative of theta with respect to the arc length parameter. Therefore, putting these together, we know that dy the theta equals dy ds times d theta ds d theta. So this is cosine theta times 1 over kappa of theta. Okay. So from here we know that y of theta, the y coordinate or the height at angle theta is equal to the integral of cosine divided by the curvature. And correspondingly, on the unit disk, since the curvature is 1, we have y star is equal to cosine times 1 and integrated. So this relation implies that y minus y star is decreasing on the interval 0 theta bar and increasing on theta bar to pi over 2, where theta bar is the angle where the curvature of omega, of boundary omega, is exactly 1. Okay? So here we use our assumption that there are only 4 vertices on the boundary of omega. Therefore, the curvature is strictly decreasing from the maximum curvature to the minimum curvature. There is no critical point for kappa in this part. Okay, so there is exactly 1 places where the kappa is exactly 1. Okay. Suppose y of theta star is greater than y star of theta star for some theta star. Then because kappa is greater than 1 before theta bar, so this star can only happen on the interval theta bar to pi over 2. And from theta star, the difference between y and y star increases. Therefore, at pi over 2, the height is greater than that of the unit disk, which means that the minor axis of omega is longer than 2. This is a contradiction to the Ionin-Pestov inequality, or a consequence of it. Therefore, we know that y of theta star must be less than y star of theta star. And looking at this picture, we have the relation of y and the length of the perfect arc we want to estimate. From the picture, we can see that the length of the perfect arc equals y times cosecant pi over 2 minus theta, which is the radius of the perfect arc. And multiply this by the spanning angle, which is pi minus 2 theta, we get L. Therefore, y of theta star less than y star of theta star implies that L of theta star less than L star of theta star. Okay, and this completes the proof of the lemma. Now we are ready to prove the theorem. We want to show that the ratio of the length of the perfect arcs in omega and in the unit disk is a function with value less than 1. Okay? And we view them as a function of the enclosed area. And some asymptotic analysis shows that when a goes to 0, L minus L star is less than 1. Okay? Therefore, the absolute maximum of this function cannot happen. So if the absolute maximum happened near the endpoint, then we are done. So we assume that the absolute maximum occurs in the interior at some a bar. So at the absolute maximum, we can differentiate this function, and by the consequence of the first variation formula, we know that the derivative of L with respect to the enclosed area is nothing but the curvature of the perfect arc. So by the quotient rule, we get this identity. And from picture, we know that L equals pi minus 2 theta over k. Here, 1 over k is the radius of the perfect arc, and pi minus 2 theta is the angle spanned by the perfect arc. So we have this relation. Plugging this into the previous identity, we get the following relation at a bar. Okay. And the previous lemma says that theta less than or equal to theta star cannot happen here. If this were the case, then we have L is less than L star, and this contradicts the identity. Okay, hence theta must greater than theta star, and this implies that L is less than L star. Okay. So this completes the proof of the theorem. And finally, let's talk about the perturbative result we obtained. We showed that the conjecture holds for perturbations of unit disk. So precisely, if omega t is a family of domain starting out from the unit disk, and each of them has area pi, then we can show that the isoperimetric profile would go down in the first derivative. Or if it's not the case, if the first derivative is 0, then the second derivative is less than 0. Okay, so this is suffices to show that the conjecture holds for perturbations of the unit disk. And the proof relies on direct computations. Okay. So we assume that we have a normal variation. Okay. Here, the tangential variation can be ignored since it doesn't affect the geometry. Okay. The picture is depicted here. Okay. We have a perturbation of a unit disk, and the perfect arc of the unit disk will experience a variation marked by the pink curve. Okay. And we assume that the variation field of sigma is given by eta times n, the normal, plus c times t. Here the notation is the same as the first variation formula of length I did in my supplementary talk to lecture 2. With some computation, we can show that the variation of the length of the arc satisfies this relation, and which in turn is equal to the following integral. Okay, here d is the length of the boundary arc, and for unit disk, everything can be computed explicitly, and we can verify the relation that the curvature of this perfect arc is equal to cotangent b, and we get this. Okay, so for each perfect arc, we have the following first variation. Okay, here, suppose we have another perfect arc labeled by u prime, then we will get something like L of u prime. Now we take all perfect arcs into consideration. The goal is to show that the variation decreases the length of one. We just need one perfect arcs. Okay, and this suffices to show that the isoperimetric profile will go down. Therefore, we integrate this variation. Okay, noting that since the variation of the unit disk preserves in closed area, therefore this normal component of the variation has integral 0, and this implies that the integral of L is also 0. If L is not identically 0, so it must be negative somewhere. which means that there exists a perfect arc with its length going down during the variation, and the isoperimetric profile decreases. However, using Fourier series, we can construct non-trivial variation such that L is identically 0, and thus we need the second variation. And the second variation is a more complicated computation, and I will not bother you with the detail. Okay, so let me finish my lecture and this talk here.